Thank you very much, Scott. Okay, this meeting is being recorded. Great. Thank you very much for this introduction. And I'm just trying to get rid of this message now. There you go. Thank you very much for the kind introduction. And it's great to be here in Oxford, well, virtually. But on the other hand, you don't have to travel, so there's upsides as well. So yeah, thank you all for coming and for inviting me. Let me start off by saying that this is really work by one of the graduate students in Edinburgh, Pinelopi Papalampidi, who's co-supervised by Mirella, Lapata, and myself. So she did all the hard work. I'm sort of just sort of the messenger here. So all the credit is hers. And also in terms of, if you need more details, there's a series of 3 papers that I'm happy to share, which talk about the work that I'm about to present. Okay, so the overall idea is to look at narrative, and more specifically to look at long, complex narrative, long, complex stories, such as they occur in movies. And in particular, we're not going to look at the movie as such, we're going to look at the screenplays, or in books, novels, and so on. Even short stories can have quite complex narrative structure. So that's what we're interested in here. Being an NLP person, we're also interested in applications. So it's of course interesting to analyze the structure of narrative for its own sake, but also we would like this to feed into applications. And these include, for example, summarization, where you take the book or the movie and you produce a short, few paragraph long summary of the narrative. Question answering, where you're able to answer questions that a user might have about a longer text. And also things like trailer generation, where you take the video of a movie and turn it into a trailer. A trailer isn't quite a summary because it tries not to give to give spoilers away. So trailer generation is quite different from summarization as a task. If we look at potential applications, then there's of course prior work that we can build on. So in summarization, for example, there's a corpus called script base, and our corpus is actually a subcorpus of that corpus that contains movie scripts, screenplays, and summaries to go with those screenplays. There's quite a lot of work on question answering for movies, the movie QA dataset, for example, the CSI dataset. CSI is a TV series. And that corpus annotates the episodes of that series with various information to do with characters, to do with plot points, to do also with summaries. There's also literature on narrative QA, which is a text-based task. Summarization and question answering are very ubiquitous in NLP, but mostly done on shorter text. So the important thing here is that this is longer narrative text, and there's far less work than, for example, on news text for summarization and QA. And then trailer generation is something that computer vision people mostly like to do. So I've mentioned that already. So why are narrative? Why are they challenging? Long, complex narratives. Well, first, sort of from an engineering point of view, there's computational limitations. Most of the models that we have in NLP, they work on the sentence level or on the level of a short text. For example, again, a news story, maybe a page or 2 in length. And it's also the approaches that we have are often insufficient because they assume sort of a standard information retrieval model, where you have a collection of text and then you're trying to retrieve a snippet of information that answers a question or that feeds into a summary from that collection of text. And as we'll see later on in the talk, this approach actually works very badly for narratives. And why is this? Well, because of structure. So, sorry, wrong button. So narratives, because they're longer text, they tend to have a fairly elaborate but also predictable structure. And the structure, for example, of a short story or of a novel is very different from the structure of a news piece. In a news article, you can basically look at the first paragraph, the first few sentences. That already contains all the important information, because this is how journalists are taught to write news stories. If you do this in a narrative, then you're doing something wrong, right? You don't want to give the game away in the first chapter and the first page even, right? So narrative works quite differently, and so models that are tuned for non-fictional text, such as news text, they don't tend to work very well for narrative. So what do we mean by narrative structure? There's two answers to this. One of them is what has the NLP literature so far meant by narrative, and the other one is what do narratologists, people who think about the theory of narrative, what is their take on the issue? So quick look at the NLP literature shows that most of narrative analysis that has been going on there has been using characters as their main unit of analysis. So this is taken from the work of Chambers and Jurafsky, I think, this figure. So you build basically a network, a graph technically of characters. Here the big bubbles are the main characters, and they relate to each other, and then you have side characters that relate to the main characters, and you get a network of characters, and then maybe these arcs in the graph, they would represent an interaction between the characters, maybe an event in which they both take part. So that has been the sort of the predominant approach. What we are suggesting here is something slightly different, something that is more high level and is simpler, and we would argue computationally more feasible. It's an analysis based on events. Basically, we are assuming a more linear structure, like here, and we would like to identify the key events that drive the narrative. So we're moving from a character-based view to an event-based view. And this is where Aristotle comes in, always in a presentation like this. So there's, of course, a long history of analyzing narrative, in particular in the dramatic literature and in the literature for theater plays. And Aristotle has a famous structure that takes the form of a triangle and divides the narrative in a drama into protasis, epitasis, and catastrophe, where the protasis is basically the setup, the part of the narrative that sets the scene. Then that leads to the epitasis, which essentially is where most of the action happens, the events that happen to the main characters in the middle part of a play, and that leads to a catastrophe, which doesn't necessarily have to be a literal catastrophe, but is a climax in the play, where the tension, the dramatic tension that sometimes is referred to as an arc, that is built up in this arc, gets resolved. And then later on, people have elaborated that. This is Freitag's pyramid, which is basically an elaboration on Aristotle's triangle, where he now actually talks explicitly about events. So he talks about an exposition that starts the narrative. Then there's an inciting force, a particular event that sets the action in motion. Then the action accelerates up to a climax, which again is a specific event in the narrative. And then there's a falling motion where the narrative action slows down, reaching a resolution, which is what Aristotle would call the catastrophe eventually. And then the denouement is basically the aftermath. So the important thing is here that this has been used to define various segments in a play, acts, for example, which would correspond to the exposition, the rising action, the falling action, and the denouement, but also important events, such as the climax, for example, and the resolution. And then you might say, well, this is, theoretical analysis that might be applicable to classical Greek plays or in general classical plays. But something very similar actually is used in screenwriting theory. And this is turning points theory. And this is what we're going to build on in today's presentation. So a turning point is a narrative moment. This goes back to work by Thompson, 1999. And these turning points, really, you can already see them here, are these important events in the narrative. And they determine the progression of the plot, of the narrative, and they're able to segment the plot into thematic units, into coherent, self-contained acts, if you like, in the unfolding play, or in this case, in the unfolding movie or screenplay. And we use a modern version of this scheme. This is based on Haag's theory of 5 turning points. And so the turning points, so the scheme, as you can see, looks quite similar to Freitag's scheme to start with. And the turning points are these colorful labels here. They're major events that drive the narrative, and they also segment it. So in this scheme, we have 5 turning points, and we have then 6 segments around the turning points. So we start up setting up the scene, introducing the characters and so on. Then the main character or characters is presented with an opportunity. Something changes in their life. They meet a romantic interest, if it's a romantic comedy, for example. That creates a new situation, which progresses the narrative. But then at some point, something changes. There's a change of plan, which leads to a slightly different direction in the narrative. Also from a viewer's point of view, it's something that keeps the narrative interesting. Then the narrative progresses again until the main character reaches the point of no return, where they, for example, fully commit to their love interest. If it's a romantic comedy, or if it's a cop movie, then they fully commit to, I don't know, chasing a certain criminal and so on. Then, of course, again, we need to make things interesting. So there's complications. And these complications eventually reach what's called a major setback, where the main protagonist, his or her opportunity, his plan is in doubt and might fail. So this is sort of the biggest spoiler in a movie, right? This is where it really becomes interesting and tense. And so the character redoubles their efforts. They make a final push, and then reach the climax, which is the resolution or the catastrophe in earlier schemes, where they resolve the dramatic tension and they reach their goal. Or it's shown that they fail to reach their goal. That would also be a climax. And then aftermath is just sort of a wrap-up, where the loose ends are tied together. And the interesting thing is that this scheme is a prescriptive scheme. So what Haag and colleagues basically tell screenwriters, if you want to write a successful movie, then you have to follow this scheme. And the application, I think, is limited to traditional Hollywood movies. So if you have something more artistic, something more art house, something more, indie in the cinema, then maybe the scheme wouldn't apply. But as we'll see, in our corpus, we find remarkably that this scheme fits real screenplays remarkably well. And we'll come back to that. Okay, so this is the scheme. I will now give you an example, just so that you can see how this applies in reality. So this is the movie Backup Plan, which is a romantic comedy. And we found that romantic comedies fit the scheme very, very well. So that's why I'm using this example here. So we have our main character, Zoe, who's basically given up on finding a relationship and undergoes in vitro fertilization. That is the setup. So oops, sorry, this part here. But then an opportunity arises. She meets the other main character, Stan, in the back of a cab, it seems. And they start dating. So again, this is a new situation that has arisen. So we predict now a change of plan. That's the next turning point. And the change of plan happens when it turns out that Zoe is pregnant. And that obviously changes the plan in the sense that it changes the relationship with Stan. She decides to tell him. Then Stan decides to commit to Zoe and the baby. So this is the point of no return, aptly named in this case. But then various problems and misunderstandings arise. And the major setback is that the two break up. Then Zoe redoubles her effort to get Stan back, and she sees signs that he still loves her. So that is here after the major setback, the final push that happens, resulting ultimately in the climax, which is when Stan proposes. And then in the end, in the aftermath, Zoe is pregnant again. Okay, so this is obviously a cherry-picked example. It's an example that fits that scheme very well. But as I've already explained, and I'll show in a minute, we actually found in our corpus of 100 movies, we found that this scheme works empirically very well. Okay, so how do we now do this on actual data? So we now basically have a new task. The task is to take a movie, for example, the screenplay of a movie, and identify the turning points. So the turning points are the colorful bits here, the key events. And the segments here we get for free, because these are just the things that happen. For example, the scenes, if we assume each turning point is a scene, then these are the scenes that happen between the turning points. Okay, so we don't need to identify those as well. Once we have the turning points, we have the overall structure. So we have compiled a data set called the Turning Point Dataset, or Tripod for short, that consists of 99 movies. And by movies, we mean we have the screenplays. These are publicly available. And we have plot synopses. Plot synopses are basically longer descriptions of the plot of a movie, typically a page or two. If you go to Wikipedia and you look up a movie, you will find a plot synopsis, which is a long description. It is not like in a review, so there is spoilers. It describes all the events, and it's longer than an abstract. An abstract would probably just be a paragraph or something like that, or a summary. And in fact, our synopses are taken from Wikipedia, so they have a fairly standardized format. And now what we did, we annotated the turning points on the synopses. So we trained 2 annotators with fairly lengthy guidelines to be able to do turning point annotation. We gave them definitions, we gave them examples, we had training sessions with them. So this is by no means an easy task, but it resulted in those 99 movies annotated with 5 turning points in the synopsis. So we didn't annotate the screenplays at first, at least, but we annotated the synopses. And so this is just our training test split. So we have 15 test movies and the rest is train, which is small. 100 movies is small. But bear in mind that the number of turning points, of course, is 5 times that. And the number of sentences and the number of scenes in the screenplays is even bigger. So it's a sort of medium-sized data set that we get our way. Okay, so the annotation, in practice, what we did, we gave our annotators a synopsis. This is an example from a movie called The Panic Room, which is a thriller. It's basically someone moves into a new house and there's an intruder and they go into the panic room to shelter, and then things happen. And so the annotators get the text and then they mark a sentence per turning point. So this, the first turning point is the opportunity. They move into the new house, and that's when the break-in happens. Then there's the change of plan. They run into the panic room. Then there's the major setback. The change of plan, and then there's I'm forgetting my own turning points. The point of no return, when it's revealed that Sarah is ill, she has diabetes. And then the major setback is when the police shows up, but they have to tell the police to leave because there's a hostage. And then in the end, there's a shootout and everything gets resolved. So these are the 5 turning points here. And these little paragraph marks, they're not given to the annotators. These are the paragraph boundaries that we get from the turning point. So we assume there's a segment boundary after every turning point. So this is the annotation task. The fact that we ask people to annotate exactly 1 sentence per turning point reduces annotation effort and also is conducive to getting high inter-annotator agreement. We have two measures of agreement. The first one is total agreement, which is really just the percentage of cases where the annotator selected the same sentence. So we double annotate, so we count how often the two annotators select the same turning points. And here we get an overall agreement of 64%, which is not massive, but given the difficulty and the subjectivity of the task, is a decent agreement. Then remember, we care about the movies. We don't care that much about the synopses, the plot synopses, but we want to look at the screenplays. So screenplay annotation is, of course, a lot harder because screenplays, the average screenplay is about 100 pages, 110 pages. So these are long documents. And so we only annotated the screenplays for the test set. Remember, we had 15 movies in the test set. And we also gave the annotators the synopses to help with the screenplay annotation. So now the task is they have to take a plot synopsis, which is already annotated with turning points, and they have to find the scenes that correspond to those sentences in the synopsis, right? So they don't have to be continuous. So here, for example, these two scenes would correspond to the first turning point. And so they do this for all 5 turning points. They have to go through the whole screenplay, read the whole screenplay. So this is, again, requires trained annotators and is a fairly lengthy task. Okay, and here we're using a different measure of agreement. This is total agreement. Oh, sorry, I went the wrong way. This is, okay, so we do it only for the movies in the test set. We use the scenes, we select the scenes that are representative of a turning point. And inter-annotator agreement, so there's a formula here, but what this basically means, it's the distance between the closest scene that the annotator has marked up and the scene that the other annotator or the gold standard scene. Okay, so it's the minimum annotation distance. We normalize this by length of the screenplay because they're not all equally long, so we get a percentage. And here our agreement is around 1.5%. So on average, we're 1.5% of the overall length of the screenplay off when we double annotate, or later on when we compare to what a system does. Of course, we can use the same measures, the annotation distance D and the total agreement TA, to also compare a system to human annotation. And that's what we're going to do, in fact. Okay, so now we have our data set. We have annotated that data set. Note that at this point, we don't actually have movies as in videos and audio, right? We are just doing this on text. I will come back to that in the later part of my talk. We'll talk about how to use audiovisual features. But at the moment, we're just doing this on text. Okay, so now we're introducing a model. As everyone else, we're using a neural network model in everyone else in NLP and computer vision, at least. And what we're doing is basically we're taking the sentences in a screenplay or in a synopsis. So we're talking about synopses first. And we call these X1, X2, X3, and so on. And we are outputting for each sentence a binary label that tells us, is this a turning point or not? So it's very simple. We encode the sentence and decode it as a binary label that indicates whether the sentence is a turning point or not. We're using a sentence encoder. This is an off-the-shelf thing that you can get in NLP in many different flavors. So if you've heard of something like BERT, for example, or Elmo, these are probably the most popular sentence encoders. We found that an encoder called USE works really well. So that's what we're going to use, no pun intended. So we're encoding our sentences. Sorry, wrong direction. And then now we have a representation for each sentence, but we want to also get a representation for the synopsis, of course. And there we use by LSTM, which is a recurrent model that is applied in a forward and backward way, and basically contextualizes the every sentence in the context of the preceding and following sentences. Then we have, this is the magic sauce. Until here, it's really all very standard. Something called the context interaction layer, which I'll explain in detail. And it's basically a way of modeling segmentation boundaries. Because if you go back to the theory, a long way back, these turning points, they not only are important events, they are also supposed to be boundaries between different acts, quote unquote, in the movie. Right here we have the setup, and then here we have the rising action, the new situation, and the progress. So there's a notable difference supposed to be between the scenes here and the scenes here, for example, or the scenes in the complications and the scenes in the final push. Right. So this is what the context interaction layer does. It allows us to model this. The fact that our turning points are segmentation boundaries as well in the text of a synopsis or of a screenplay. So how does the context interaction layer work? So here I'll focus on one particular sentence, call it X3, and these are the context sentences preceding and following it. We slide another layer. This is just a normal feed-forward layer. We slide this across the context leading up to X3, which is the sentence we're interested in, from the left and from the right. So we get a representation of the left and right context of our sentence. We then do similarity computations between this context representation here and the representation of the sentence X3 that we're interested in. And in fact, we try a bunch of different similarity measures and put them all in. They all help a little bit. And then we output a representation that is just our initial sentence. Here, the purple dots are the representation of X3. And we have a representation of the similarity with the context to the left and the similarity with the context to the right. And then we concatenate all of this, and this then feeds into our classifier. Remember, we're outputting a binary classification whether X3 is a turning point sentence or not. Okay, so this is the context interaction layer, which sits here on the top of our sentence encoder. And now we're almost done. We do one more thing. We assume, of course, that all these turning points, they don't all behave in the same way, right? So what we can do, we can build a separate encoder for each of the turning points. So we actually have 5 encoders. They all have this structure here that I've just explained. And we merge them in a merging layer, which is just a fully connected layer of the output of each of these encoders. And then we predict the turning point status, again, binary, yes or no, for each sentence from Y1 to YN, where N is the last sentence in our synopsis. So now you may be asking, this is fine. In your input, you have your turning points, but in your output, you just have binary classification. Well, we're not actually predicting the turning point labels. So we're not predicting this is the point of no return, or this is the climax or something like this. We're just predicting this is the first turning point, second turning point, third turning point, because we're assuming there always are 5 turning points and they always occur in the same order. So with those assumptions, we don't actually need the labels. We just need to predict those 5 turning points. So in reality, what this means, we just take the 5 sentences with the highest probability of being a turning point and assign them the 5 labels in sequence as predicted by the theory. So this gives us the overall model. Now the question is, does this model work? Oh, okay, sorry. Now what do we do when we have screenplays? So this model just predicts turning points on synopsis sentences. So it pulls out 5 sentences that represent the 5 turning points. So let's assume we have this, right? So we now have a synopsis that is annotated with turning points, and we will actually experiment with gold standard annotation, because remember, on the training set, we have gold standard annotation for the turning points, and with predicted annotation. And based on that, we're now trying to predict the turning points on the screenplays. And remember, for screenplays, the turning points are scenes, or rather sets of scenes. So here, for example, for TP1, we have 2 scenes that correspond to that turning point, right? So we can either do that. So it's basically a correspondence problem where we align the synopses with the screenplays and align the turning points that are marked up in the synopsis with the screenplay scenes that represent them. Okay, we can do this on the gold standard turning points. This is technically called annotation projection in NLP, or we can use it on the predicted turning points. So we go straight from the text to the annotation. This is called an end-to-end model. Okay, so now we have a problem, because if you remember our annotation, we had our 99 movies and we annotated them for turning points in the synopses, but we annotated the scenes only in our test set. Obviously, we cannot use the test set for training, so we don't actually have annotated turning points in our screenplays. So what do we do? Well, theory comes to the rescue. If you remember Haig's turning point theory, which is directed towards screenwriters, but so far has turned out to be very useful also for annotating synopses. So this theory actually not only claims that there is a fixed number of turning points and they occur in a certain order, but it also tells you where they occur. Specifically, it gives you a percentage of a screenplay where you should have a turning point. Remember, again, this is prescriptive, right? So he is telling screenwriters what to do. And he says, turning point 1, remember this was the opportunity, should appear 10% in. So 10% in terms of the page count or the word count, or the count in terms of minutes if it's a movie. Turning point 2, which is the change of plan, should occur after 25%. Turning point 3, which is the point of no return, after 50%. The climax after 75%. Sorry, the major setback after 75%, and then the climax after 94.5%. I don't know why it's that exact number, but that is the theoretical stipulation. And now we can, of course, check in our data set. Remember, we have now 99 plot synopses annotated with turning points. We can check what is the empirical distribution. So this is the mean position of these turning points, and this is the standard deviation around that mean. So we get a pretty good match. Turning point 1 empirically occurs after 11% of the screenplay. Turning point 2 empirically occurs a bit later, after about 32%, rather than theory predicted 25%. Turning point 3, which is the point of no return, exactly in the middle of the movie. And this is what the theory said. You should have the point of no return in the middle of the movie, and that's what we find in our synopses. Same for the major setback, almost exactly 75% in. The climax occurs a bit earlier, after 89% than predicted by theory. We also see some differences in how variable these are. So TP2 and TP3 are actually quite variable, as you can see from the high standard deviation here. Whereas, for example, the climax, that is pretty fixed where that occurs, and also for the opportunity. So what we can now do is to take this empirical distribution, the mean and the standard deviation, and use this to select scenes. So we basically say the turning point scenes in our screenplay are the ones that occur at 11.4% at that point in our screenplay. And we select actually a window of around 3 scenes around that point in the screenplay. And these are our turning point scenes. This is obviously not the same as using actual human annotators and doing manual annotation, which is reliable, but this is just an approximation, right? So this is a heuristic that helps us generate training data without having to annotate all 99 screenplays. All right, so we just basically, again, do binary labeling. For each turning point, we label a scene as relevant if it's in this window of mu plus minus sigma, or irrelevant if it's not in one of those 5 windows. Okay, so now we have some, let's call it silver standard data annotated for scene labels. So that means we can now build a model that predicts turning points for scenes rather than just for plot synopsis sentences. And this is the model, which is very similar to the original model. We again start with a sentence encoder for our synopses as before, but also for our screenplays. Of course, the screenplays also contain sentences. We then have our by LSTM to encode the synopsis as a whole or the screenplay as a whole. And for the turning points, we're done because we have our turning point labels, right? So we no longer need to predict the labels in this approach. We assume that we have the turning points either using the previous model, right? We've predicted them using this model, or if we, in the gold standard setup, then we're using the human annotated turning points here. And the screenplay encoder then uses remember our context interaction layer, which is a way of saying, is this scene similar to the scene before or after, or should there be a boundary? And the boundary would be a turning point, right? So that is useful also for the scenes, not just for the synopses. And then we have an interaction layer where we concatenate our representation for the screenplays with the representation for the turning points in the synopses to be able to compute similarity. So we get similarity vectors, basically saying this scene is similar to TP1 to this extent, similar to TP2 to that extent, and so on. So we get a vector of similarities. It's actually a matrix of turning points by scenes. And this we then feed in a binary classifier. The binary classifier tells us for each scene whether it should be a turning point or not. So same overall idea as in the sentence classification for synopses. Okay, so how does that work? Does it work in practice? Let's see some results. So at training time, as I said, we use an existing sentence encoder called use, which is basically something that you can pull off the shelf. It's readily trained. You just apply it to a sentence and you get a vector out that represents that sentence. In terms of inference on the synopsis, we force the model to predict one sentence per turning point, so 5 turning points in total. On the screenplays, we force it to predict around 3 scenes per turning point. These are basically, if you think of the maximum, right? So here, what we get out, in fact, is not just a binary label, but we get a probability as well. So we take the maximum of that probability and take the 3 scenes with the highest probability. 3 is an empirical value. That's roughly how many scenes our annotators selected per turning points when they annotated the test set. Evaluation, we can use the same evaluation metrics that we use to measure inter-annotator agreement, namely the total agreement, which is simply how many sentences do we get right, or the distance, which is how close are we to the correct sentence or the correct scene in a screenplay. Okay, so just to remind you, so this is now turning point identification. That's our first task. Take a synopsis, identify the 5 turning points. Human agreement is around 64. So this is basically as good as it will get, right? We wouldn't expect our model to be better than human agreement. Let's first look random. If we just select 5 sentences at random, that really doesn't work. If we select the 5 sentences that fall on the theoretical positions, 10% in, 25% in, and so on, then we're doing reasonably well. We get 22% correct. The distribution baseline, where we now take the observed positions rather than theoretical positions, remember these were slightly different, we get a 28% correct. And then our model, which is this model here, the multi-view topic-aware model here, we get a performance of around 38%, 39%. So it's off of human performance by quite a long way, but it's also significantly better than our baseline. Okay, so now we have a reasonable way of predicting turning points in synopses. What about screenplays? Oh yeah, sorry, first, we also have a human evaluation study where people have to rank the sentences produced by the various models. And what we find is in the gold standard, 40% of the time it's ranked first, 70% of the time it's ranked second, and the rest of the time it's ranked third. Our model is ranked about 30% first, and if you take first and second position, it's about 70%, same as the gold standard. And the distribution baseline is significantly worse. So that's the important thing. It's ranked first less often, and it's also ranked second less often than our model. Okay, but now let's look at the scenes. Can we do turning points on scenes? So now we have a different evaluation metric. Now lower is better. That's the important thing. That's why there's this little arrow. So this is percent difference from the true position of the scene in the screenplay. Okay, so the lower the better. Humans are quite good. They're within 1.5% of the true position. Theory baseline and distribution baseline are doing okay, but not, not dramatically well, around 10% off. So if, for example, the point of no return is that it's supposed to be at 50%, then they would predict it at 60 or 40% on average in that distance. I mentioned initially that we should also think about information retrieval models. An information retrieval model, of course, is applicable for this because we're basically taking a screenplay and we're extracting sentences, or we're taking a synopsis and we're extracting scenes, or we're extracting sentences from a synopsis. So this is a classic information retrieval task. And so we can use information retrieval models such as TF-IDF, which is sort of the simplest model you can get. It actually does worse than the baseline. In the full paper, there's other IR models as well, which I'm not going to go into, but this is sort of the most representative one. So then drum roll, how does the topic-aware model do? It does at around 9% difference. So it's quite a lot worse than human agreement, but clearly better than the IR model and the baselines. This is assuming gold standard turning points. So remember, on our training set, we actually have the gold standard turning points, so we can use those, and then we get a 9%. If we also have to predict the turning points, using the previous model, this model here, then of course we're going to take a hit. In this end-to-end setup, it goes down to around, well, it goes up to around 10% difference, which is still slightly better than our baselines, but not much. Bearing in mind that we don't have training data, right? We don't have training data for the scenes. We only have the training data for the synopses. Okay, so this is okay, but not great. And this is something we'll come back to in a minute. Can we improve on that? But before we get there, let's look at how this actually looks like. So here we don't have actual movies, but we have diagrams that visualize screenplays. So on the x-axis, we have the scene index. So this screenplay is the movie Juno, which is sort of a coming-of-age movie. We have around 110 scenes in that movie. And here are where the turning points would fall according to our distribution baseline. Okay, in this movie. So this is what we get when we take, oh no, sorry, this is the, these are the gold standard annotations, sorry, not the theory baseline. So gold standard annotation means a human has taken the synopsis and has taken the synopsis, annotated that with turning points, and then they have also taken a screenplay where they have annotated the scenes, right? Remember, we have 15 movies where we have the annotation for both on the test set. So these are then the turning points as annotated by our human annotators. And then we can compare this to the theory where the turning points are supposed to be predicted. And we've just taken that fraction and drawn a Gaussian around it. So this would be 10% in. This would be the opportunity. In fact, the opportunity happens earlier in this movie. This would be the change of plans, which also happens slightly earlier in this movie. The point of no return. Also, the setback is almost as predicted by theory, and the climax is later than predicted by theory. Okay, so these are the expected turning points, whereas the real turning points. And now let's see what our models do. So this is our enemy, the TF-IDF baseline, the IR baseline. And not only does it not work so well, as we saw here, but also the predictions are way off in the sense that turning point 4 is predicted to be somehow everywhere, right? And the green one, turning point 2, also, there's multiple spikes. So clearly this is not the right way to model it. And in particular, if we then compare it to our model, the TAM, we get these distributions, which again is the cherry-picked example, obviously, but the message is that they are relatively close to the gold standard positions, and they also show a sensible distribution around those positions rather than being all over the place, as in the TF-IDF baseline. Okay, so here, for example, for the let's take the point of no return, which is unusual in this movie, is actually well predicted by our model, whereas the theory baseline would predict it later, and you can't even see the point of no return. Here's a spike that corresponds to the point of no return in the TF-IDF baseline. Okay, so to conclude the first part, this is an interim conclusion. We've introduced a new task called turning point identification in screenplays. We've generated a data set that consists of 99 movies with turning point annotations in their synopses. And we've introduced an end-to-end network that can do turning point identification first in synopsis, but then also in screenplays. Why turning point identification? Well, it's a way of finding the key events in screenplays, and it's also a way of segmenting the narrative into thematic units. Okay, so this is all fine, but something's missing. So two things. First of all, what about multimodal information, right? So we're just talking about text so far. And secondly, are these turning points actually useful for applications? Remember, I've said this can be used for question answering, can be used for summarization. I've not actually shown that. I've just shown you how to pull out turning points. So in the last 5 to 10 minutes, let's talk about that a little bit. And this is more preliminary work. It's currently unpublished work, a bit less polished, etc. And I will also go through that fairly quickly. Okay, so let's look at that. So there's actually a simple way which we can use to turn turning points into summaries. We can just use them to extract scenes, naively by saying, okay, so we have the scenes that correspond to the turning points. Let's just pull out those scenes and say this collection of scenes is our summary. Just stick them together, right? Each turning point corresponds to between 1 and 3 scenes. Pull them out, cut them together. That's our summary. So we have a video summary of our movie that way. The only thing we need to do is align the screenplay with the actual video, which actually is not so trivial, and I can talk about this in the question period if you're interested. But let's assume we can do that, and then we can get a summary that would work. This is slightly more formally how we do this. So for each scene, SI, in a screenplay, we assign a binary label, YIT, which is indicating whether this scene, YI, represents turning point T. So this is exactly what we've done with the model we've seen so far with the TAM model. So the TAM model gives us a probability over the conditional probability of a scene SI being the turning point YIT. Okay, so we can get a summary just by selecting consecutive scenes on the peak of the maximum of this distribution for our 5 turning points. So T ranges over the 5 turning points that we have. Okay, so we don't actually need to do anything else. And the question is, would this work? We'll answer that question later on. But before that, let's try if we can develop a slightly more interesting model to compare the simple model to. The problem with the TAM is that it assumes a very simple linear structure, right? Turning point 1 followed by turning point 2 and so on. The scenes are linear. We just look at the neighborhood of each scene. We decide whether each scene is a boundary or a turning point, but we don't capture the fact that a scene in the introduction might then relate back to a scene at the climax because some important information was introduced there, which is then used to resolve the overall conflict in the climax. So the structure of a screenplay is actually more complicated than a simple sequence, a simple linear structure. So what we're introducing here are screenplay graphs. And I will tell you how to compute those graphs, but also then these graphs can be used to compute our probability, right? The same probability that the TAM computes, but better, as I'll show. And we can then use this for generating summaries as well. So what is a screenplay graph? What does it actually represent? Well, the nodes in the graph are supposed to represent the scenes, and the edges represent how similar they are. And now also, remember, I promised you some multimodal stuff. So now we're going to use both textual and audiovisual features to formalize similarity between scenes. Okay, so here's a high-level schematic view of what we're doing. So now we're taking the screenplay, the text, and the video of the movie. We turn this into a graph. The graph represents which scenes are related to each other, and these don't have to now be linear. They don't have to follow each other in the screenplay. On that graph, we do turning point identification. So here the colored bits are the turning points, and then we just pull out the turning points, and that's our video summary. Okay, so that's the overall approach. So let me tell you a little bit about the nitty-gritty. How does this actually work? So we start with a fully connected graph. That means we take one node for each scene and we connect them all to each other. So every scene is connected to every other scene. Then we devise a way of measuring the similarity between scenes. So taking a pair of scenes, this tells us how similar these scenes are. And we use both textual and audiovisual information to compute similarity. And using the similarity measure, we can now sparsify the graph. So that means we can remove edges to only leave the top k neighbors of each node, of each scene. Then we encode this sparse graph in a fancy machine learning approach called graph convolutional networks. These are basically neural networks that allow you to not just encode a sequence, but encode a graph through a way of formalizing the neighborhoods in the graph. Then out of the GCN, we get a neighborhood representation. We merge this, we concatenate this with the scene content representation, which is very similar to the representation we've seen in the first part of the talk. And then we can use a classifier and use this representation and predict our distribution over turning points as before. Okay, so this is a diagram that illustrates this a little bit more. Okay, so let's think about the input. The input is the text, but also the video and the audio. The audio, there's actually audio embeddings that are again off the shelf, similar to the text embeddings. Video is more complicated. We are extracting key scenes, and then we're doing feature extractions from those key scenes. So we get a representation of the video that way. And based on the audio and the video features, we compute audiovisual similarity. Based on the text features, so these are our scene representations, just like in the first part of the talk, we now can compute similarity between pairs of scenes. And so we get an overall similarity measure. We apply this to our fully connected graph, right? So this is all the scenes connected to each other. And now each of these vertices in our graph represents the similarity between those two scenes. We sparsify this using the top k neighbors. So we get this blue graph here. We encode this in the graph convolutional network, and we get an overall neighborhood representation, which we concatenate with the scene representation. And that gives us a representation for each scene, which we then feed into our classifier that predicts whether that scene should be a turning point or not. Okay, so the overall idea is the same as in the TAM-based turning point prediction, but we just have a more complicated structure where we can take more complex neighborhoods into account rather than just preceding and following scenes. Okay, does this actually work? So here I have a table that now presents the total agreement, but also the distance. Remember, total agreement, higher is better, distance lower is better. And we are doing this now on scenes, right? this graph construction doesn't really make sense on sentences in a synopsis. So everything is done on scenes now. So random baseline assumes even distribution. The theory baseline, this is actually a slightly different data set. So the results differ slightly from the ones I presented in the first part. So this is how well the theory baseline does and the distribution baseline. Now, jumping straight to TAM. So TAM again beats our baselines here in terms of total agreement, but it also beats the baseline in terms of distance. So we get a lower distance than the baselines. And now the question is, what happens when they add our audiovisual features? So we can just remove this bit here and just get a text-based model. And turns actually out TAM doesn't benefit from the audiovisual features. TA goes down slightly and distance goes up slightly. And now let's compare this to the graph model. So this is this model. TAM is the model from the first part of the talk, right, where we just have a linear structure. And now graph TP is the graph-based turning point model. And here what we find is we get a decrease compared to TAM if we just use text features. But if you add the audio visual features, then this goes up to 9% total agreement. And in terms of distance, the distance actually, we're not able, we see a small reduction actually with the audio visual features again. But we basically match TAM in terms of distance. We don't get an improvement. We do, however, better our baselines. So that's great. And in particular, I've introduced also two other baselines here. These are summarization models from the literature. Because if you want to publish this in ACL or in some other NLP conference, people will always ask, so how does this compare to a standard off-the-shelf summarization model? And here we have two text rank, which pulls our sentences, and scene sum, which is the same, but for larger texts. And you can see it's far worse in terms of distance and also in terms of TA than our best performing models here. The graph TP with audiovisual features or TAM without audiovisual features. Okay, to summarize this, graph TP is able to outperform TAM on total agreement. On distance, it's roughly the same. It doesn't outperform TAM. The TP-based approaches clearly outperform the existing unsupervised summarization models, right? Those two here. So there's clearly something gained to be gained from having turning points in the mix. And we get some improvement from audiovisual features, but to be perfectly honest, we would have hoped this to make a bigger difference. So this is something we're investigating. And for TAM, for example, the audiovisual features don't seem to help. Okay, now one more set of results. These are just evaluations on turning points, right? We again testing whether our turning points are correct. Are our summaries actually good summaries? Remember, we can just turn the turning points into summaries by pulling out the scenes that correspond to the turning points. So we've done a human evaluation study where we gave people summaries, which consist of 3 consecutive scenes for each turning point. So these are actually movies or summaries of movies that people played. They are about 10 minutes long. And then the annotators had to decide whether the relevant information for each turning point is correctly included in the summary. So that's a yes or no decision, and rate the overall quality from 1 to 5 of the summary. So here we're so these are the 5 different turning points. This is scene sum, which is one of the existing summarization systems. This is TAM, this is graph TP, which is our graph model. And this is the gold standard annotation. So what we can see is that TAM, except for turning point 1, is always better than scene sum. And graph TP actually massively improves over TAM. So whereas in actual turning point identification, the difference wasn't very big, but regarding whether the correct information is included, there's a big difference. So the mean goes up from 30 to 50 compared to a gold standard mean of 57. So the human evaluation shows that the human annotators really like those summaries. Then we also evaluated not just the turning points, but the overall quality of the summaries. And TAM is similar to scene sum, but GraphTP gets an improvement. This is on a 1 to 5 scale. And of course, the human summaries are also. They're not perfect with a rating of 3.6 approximately, but they're better than the GraphTP summaries. Okay, and now we can do fun stuff with the graphs. So because remember, we turn our screenplay into a graph, and we can of course look at these graphs. We can use them for identifying turning points or for doing summaries, but we can also look at them. And in particular, what we did here is the connectivity of the graph, of the turning points. So connectivity is you take the node in the graph and you count how many connections do you need to cut before you have a clique, an unconnected subgraph. Okay, so this is a standard measure in the graph analysis literature. And so what I've graphed here is the connectivity on the y-axis and the turning point on the x-axis. And it turns out that there's quite a big difference in terms of genre, in terms of connectivity. So thriller and mystery movies have typically an unconnected or fairly low connectivity screenplay graph. Drama movies have a slightly higher degree of connectivity. Comedy and action, at least initially, have a high degree of connectivity, which then goes down though. And the most connected movies tend to be action movies. So this could be because the different parts, right, the 6 different parts are not very different from each other. There's basically car chases everywhere. So that could explain this high degree of connectivity that we find in action movies. These labels, by the way, are inherent in our data set. So we didn't make these up, these genre labels. So these come with the screenplays. Okay, so that is very interesting, and we can visualize this, for example, by looking at individual movies. So this is Die Hard, classic action movie. You can see the turning points here. These colorful dots are the turning point scenes, and the gray dots are the other scenes connected to the turning points after sparsification, right? Remember, we are removing some scenes. And you get a good degree of connectivity. Comparing this to American Beauty, which is comedy, drama, something like that, you get a lot of unconnected cliques, right? So here, for example, you have the same type of scenes in the 2 different cliques, and then there's only one other type of turning point there. So you get quite a different setup between movies. So it is interesting to analyze these graphs, and this is something we would like to do more of. So there is a connection with genre, it seems, but this is something we would need to investigate more. Okay, to summarize, I've introduced the tripod data set. I've tried to convince you that turning point identification is something that we should be doing to analyze narrative structure. And then I've tried to convince you that scene graphs are a good way of representing how the different scenes in a screenplay relate to each other. They give us a natural way of incorporating audiovisual information because that's a form of similarity, or can be used as a form of similarity. They allow us to compute turning points more accurately, and they can be the basis for movie summarization. And hopefully in the future, will also support content analysis. We've seen the effect on genre, for example. That's all I have. Thank you very much for your attention.